Welcome back to the CT Reconstruction Series. In Part 1, we generated a realistic fan beam sinogram from a Shep-Logan phantom. Today, in Part 2, we'll take that sinogram and reconstruct the phantom using filtered backprojection, the classical algorithm that powered the first CT scanners. Backprojection by itself just smears each projection back along the rays, which produces a blurry image. To correct that blur, we apply a filter, the so-called RAM filter, in the frequency domain before backprojection. That's why it's called filtered backprojection. Our setup is a 2D fan beam geometry with source axis distance 570 mm, so on and so forth. These are the exact parameters we used in the projection setup, so the reconstruction matches perfectly. So now let's switch to the code. And here you can see we first set up the geometries exactly the same as we generate projection data. And here is our reconstruction matrix. We set the pixel size to be 512 by 512. We load our projection from the projection file we previously generated. And we apply the RAM filter. So in frequency domain, we use multiplication. And here in image domain, we use convolution. Then we reconstruct the image to back project the filtered projection data. And here is the loop over all the detector elements, the angles and the detector index. And finally, we saved our image to a raw file, and we will use ImageJ to visualize. So now let's run it. And it will take a minute. This 2D filter backprojection runs just fine on the CPU, and it's great for demonstration. But in real 3D cone beam CT, the problem explodes. We are talking hundreds of millions of voxels and thousands of projections. Doing that with nested loops on the CPU would take hours. That's why all practical 3D CT reconstruction is GPU accelerated. Now the reconstruction finishes. Let's use ImageJ to look at the reconstruction. We again use the import raw function, and this is our newly reconstructed image. We open it with 512 by 512, and here you see a crisp Shep-Logan phantom reconstructed entirely from our simulated sinogram. So that concludes Part 2, Filtered Backprojection. In the next part, we'll explore how noise and limited projections affect reconstruction quality. And later, we'll look at iterative methods. If you found this helpful, don't forget to like and subscribe to follow along with the rest of this series. Thank you for watching.